Okay, hello everyone, and it's time for another optimization video. So in this one, I'm going to be looking at triangles. So I've been looking at cylinders in my last two optimization videos, but this one's a slightly different approach. Okay, so what's happening? Well, let's just say that Peter is on a rowboat at position B and is 5 kilometers out at sea from this position A, which is the very western end of the beach, and what's happened is he's rowing outwards towards X, where X is some point on the beach, and the length of this beach is 6 kilometers. So now that he's pretty much gone along this, we know that he's actually going to be able to row the boat at a speed of 8 kilometers per hour, and he's going to be rowing along from BX and X to C. And he's going to be running along the beach at 17 kilometers per hour. So we got some information about the velocity there, we got some information about where he's rowing, and we got some information about the beach, but we have an unknown variable, which is x. Now the first question asks us to justify why x, so asks us explain why, and asks us explain why 0 less than or equal to x less than or equal to 6. Okay, and when it comes to these sort of explanation questions, in fact, hopefully you can read down the board, but it says 0x6 there. Essentially what it's asking us for is it's asking us for what does x mean in context, and how do you know what x means in context? Well, when we think about it, length AC, the entire length for that straight sandy beach is going to be 6 kilometers, and we just happen to have that as an upper limit. And we just happen to know that, of course, x is some length on that AC. It's an AX that's part of AC. It's a segment on AX that is going to make up part of AC. Well, if we think about that, and hopefully I'll just adjust the light. Yep, that's probably a bit nicer. But when we think about that, if x is some length on there, then the absolute minimum x can be is 0, because naturally it could just be AC and he rows in a straight line and then runs down the beach. Or the maximum it could be is 6, meaning that x kilometers is 6, so it's just pretty much going to row from B to C. So that's what it's sort of asking for. Do you understand the context? And that's why x is between 0 and 6, because it's the length on the sandy beach, and of course it can either be nothing, meaning he goes from A to B, that's the absolute minimum value x can be, and its maximum value that it can be is 6, because of course the entire beach length he could pretty much not run at all and just row to there. But given the fact that he runs faster than he rows, it's quite possible that x is going to lie somewhere in between those values. So let's just have a look through and at the next question and see what it asks us. The next question asks us, sorry about this, next question asks us to show that t of x, which is the time, the total time, is given by the square root of x squared plus 25 on 8 plus 6 take x on 17. Okay, so when we think about this, we've got a triangle and we've got a straight stretch of land. Remember in the context how he's going to be running the last little stretch from x to c, and he's going to be rowing from b to x. Well, that means we're going to need to calculate how long it takes for him to go along there and down there. So when we think about it, we've got all the information we need, we just need to be able to apply some of the relationships that we have. So, if we know that if this is total time here, then what we can do is we can think about how they got to it. And remember that this is time here, so we're going to be thinking about the displacement time function. So, if we actually have a look at this equation here, in fact, I'll start off from the very basics. You've probably heard that v equals s over t, where velocity equals displacement over time. Well, what we're going to need to do is rearrange this. So time's out the front, and therefore we've got an understanding of what's happening there. So therefore, Vt equals displacement. And that's just a vector notation there. But our Vt would equal displacement because we're bringing t from the denominator on the right-hand side to numerator on the left-hand side. And therefore, what we have is we have t equals s over v, because we're bringing the v term from the numerator on the left-hand side to denominator on the right-hand side. Okay, so now that we've sort of got an understanding of, okay, we're looking at the time function here, we're going to be able to work out how they were able to piece this together, and we're going to be able to show it. So there we go, we've verified what the time function is, and now we need to consider displacement. Well, you may remember Pythagoras' theorem, and Pythagoras' theorem says the length c, if we have a and b, and this is length c here, with the hypotenuse I will write actually, just to generalise it a bit more, the hypotenuse equals a squared plus b squared, but it's the square root of that. In general terms, hypotenuse squared equals a squared plus b squared. Okay, so now we can see that one length is 5 and the other length is x. So if we substitute this in, because of course we want the hypotenuse, we see that the hypotenuse is equal to the square root of x squared, because again, it's a squared, a is our x value, and then it's also b squared, and b is 5 kilometres, because that's that side there. Remember ACB, you've probably heard that notation of Pythagoras' theorem before, so that's one I'll use, and that's how we get the hypotenuse. And this is also the displacement, believe it or not, because, well, this is the distance that they travel. That is the length of the hypotenuse. And as you can see here, that's the numerator of the very first part of our t of x function, our time function. Okay, so we know why that's in there, because if we look at our displacement, time function here, we get s and t, or should I say our time equation, we have s and t there, and our displacement's on top, and we've got our displacement there. So that's going to be the displacement of the triangle there, the hypotenuse, or the distance that he rows when he's rowing from point B to point X. Okay, and now what we have to consider is, of course, the velocity part of it. Well, we know that he can row at 8 kilometres per hour. Now, because that's obviously, because we're working with kilometres here, because of course that's x kilometres, that's 5 kilometres, then that means that it's just over 8, and that's where that 8 in the denominator comes from, because that's the velocity underneath. So we could pretty much draw out these steps. You could say that, and then you could say something like velocity equals blah blah blah, and you'd have this verification there, and that would help you prove that that's our t of x function. So where does the 6 over x come from? Well, entire length for this A to C length, is 6 kilometres. And he's only running from X to C because, of course, he's rowing that part. So, because that's so, that's 6 take X because he's not running this part, he's just running that part. So we have 6 as being the total length, take the X that he doesn't run, and voila, we have displacement. Again, you could have similar sort of justification there, but I'm just going to explain it in this video. And then the 17, again, because we're all working with kilometres, and he gives how fast he can run in kilometres as well, it's just divide 17, because again, time equals displacement over velocity. Wow, okay, that's awesome. We understand why that t of x function came about, and we're able to take the derivative of it, because the next question is going to, of course, ask us to optimise it. So he knows exactly where position x is, and because he knows where position x is, he knows what he should row and then what he should run. Okay, so in order to take the first derivative of our t of x function, what we do is we just simply apply quotient rule in both cases, and hopefully you are reasonably familiar with quotient rule. Okay. So, in order to do quotient rule, what we do is we take the derivative of the numerator term. So the t of x equals, and we take the derivative of this, so it's going to be half x squared plus 25 to the power of a negative half lots of 2x multiplied by the denominator, which is going to be 8. Now you're probably thinking, how did I get that? Well, I just applied chain rule. We bring the exponent out the front, and then we subtract 1 from the exponent, but we write the actual part underneath this, because again we can imagine this as being in brackets to the power of half if we wanted to, and from that we just write whatever the derivative of anything in the brackets is. Of course we bring the 2 down in front of the x, so it's going to be 2x, and we multiply it by our denominator, because it's the f prime of x, then gx. If you need to touch up on quotient rule, I really recommend that you do. Have a look at it, and then you come back to this and you'll be able to understand how I got that. And then we take the g prime of x, which is 0, because the derivative of the constant is 0, so we just cut it off there, because 0 times by the numerator as it is just going to be 0. And that's all over the g of x squared, so it's over x squared, which I'm going to go ahead and simplify to 64, because of course 8 times 8 equals 64. So now from this, and it looks like it just fits on there, which is pretty good, but what we do is we take the derivative of our second part. So let's think about this. We have 6 take x in the numerator, so of course it's going to be negative 1 as the derivative there. So this is going to be negative operation in between. So it's going to be negative 1, I won't even bother writing 1, lots of the denominator, and then we just do, we take the g of x squared, which of course, the g of x, the g prime of x, sorry, and the derivative of a constant is 0, so we take 0 lots of blah blah blah, which is where blah 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 is the numerator, so we just leave it at take 17, and then of course we square the denominator. And therefore we have our, oops, I'll just denote that with a prime, we have our t prime of x. And you can probably just see that on the video. Well, now what we need to do is we need to be able to optimize this value. And in order to optimize it, we need to set the first derivative to 0. Now, why do we set the first derivative to 0? Well, if this is our t of x function, and you imagine this on a graph, there would be a value where x is the time is the smallest, wouldn't there? Because you're changing this length, and as you change this length, the amount of time it takes a Peter to do something increases or decreases. Say if I brought this to here, and obviously he'd row at 8 kilometres here, and then he would run 17 down there. If we brought it out to there, he would row 8 from there to there. And again, we need to try and find that balance so it takes him the least amount of time based on how fast he can run. And that's what we're doing. So when there's a minimum x value on our t of x function, this means that that's the minimum distance, or the distance which will result in a minimum time. So we set the x kilometres to that much, so Peter knows where he's rowing to on the beach, and he'll be able to do the entire circuit within the smallest amount of time. So when we take the first derivative, this value is going to be equal to 0 because essentially the derivative function shows when a slope is increasing and decreasing. So when the derivative is positive, that means that the slope is going to be increasing. And when the derivative is negative, that means that the slope is going to be decreasing on our original function. So it's when the slope's equal to 0 that we have what's called a stationary point. Think of it as being the slope of the tangent having no slope. The slope at a given point having no slope. That's going to be obviously a minimum, because if we draw a graph, there's no slope at the minimum. And that's why we set the first derivative to 0, and that's why we do it here, because we want to be able to find the lowest value of x. Because the question asks what's its significance, and I've just sort of explained what significance is now, because I'm sort of running out of time to actually do it. So in the next video, we will be finding the value where the derivative equals 0, the x value, and from that we'll be able to check if it's a minima. And if it is a minima, then Peter's going to be able to row and run down this beach in the shortest amount of time. So hopefully that video covered a few things. The part 2 video will be coming very shortly. Thank you for listening, and I'll see you then.